Hello, my name is Sankararaman from the Department of Chemistry at IIT Madras. This is the second lecture in the Organic Chemistry Fundamental Concepts lectures. In this particular lecture, we will consider two aspects. One is nomenclature of organic compounds, simple organic compounds, how to name them, and secondly, we talk about the concept of isomerism in organic compounds. Now, carbon atom has the ability to combine itself to form long chains of carbons. For example, you have methane, ethane, propane, butane, you can go all the way up to longer chains of 10 or 12 carbon chains. Essentially, each one of these representing a carbon. So, this would be 2, 4, 6, 8, 10, 12. So, this will be dodecane. C12 chain is what we are representing. So, because of this property which is known as catenation, the ability of carbon to bond with itself forming long chains, millions of organic compounds can be formed. Just as hydrocarbon, one can imagine so many. So, if we incorporate heteroatoms like nitrogen, sulfur, phosphorus, silicon and so on in the carbon framework, you can imagine innumerable number of compounds can be synthesized. So, there is a need for systematically naming the organic compounds. And the International Union of Pure and Applied Chemistry, which is known as IUPAC, International Union of Pure and Applied Chemistry. It is an organization, international organization. It has come up with certain rules and regulations to name systematically organic compounds. However complex the structure may be, there are ways of naming the organic compounds systematically, so that once we know the systematic name, we can reproduce the structure of the organic compound safely without any mistakes. So, let us start with simple alkanes. This is called methane. So, the corresponding radical would be called CH3, which will be methyl radical. This is ethane. The corresponding radical C2H5 or CH3CH2 would be called ethyl radical, ethyl radical. This is propyl. This is propane. This is butane, and so on. So, corresponding to the homolog series of C1, C2, C3, C4, the next homolog series will be pentane, hexane, heptane, octane, nonane, decane, undecane, dodecane, tridecane and so on. So, the corresponding C20 H42, this correspond to Cn H2n plus 2 rule, which is the saturated hydrocarbon molecular formula, for example. So, this would correspond to ecosane. C30 H62 would be corresponding to the name triacontane. So, the hydrocarbons always end up with the A and E as the terminal name of the compound is ending up with ANE, AN. Penta means 5, buta means 4, propa means 3, etha means 2, metha means 1, and so on. That is how the hydrocarbons are named in the IUPAC system of nomenclature. Now, if you consider branched systems like this, for example. Now, let us talk about a simple branched system which is only one branching in this particular position here. In a branched system like this, the longest carbon chain is taken and the number is given from the longest carbon chain closest to the branching. So, this is the parent hydrocarbon is pentane and in the 2 position there is a substituent which is the methyl group. So, this is 2-methyl pentane. One can do a mistake of naming it slightly differently, which would be the wrong name for this particular compound. Instead of starting the number from the right hand side to the left hand side, one can start from the left hand side to the right hand side and call it as 4-methyl pentane. This would be a wrong nomenclature because substituents where the branching is taking place is always given the least number that is possible. So, this is 2-methyl pentane and not 4-methyl pentane. So, that is rule number 1. Branched alkane, longest chain is taken and then numbering starts closest to the branch. Let us illustrate this with one more example also. You consider, for example, a heptane So, the longest chain if you consider here would be 1, 2, 3, 4, 5, 6, 7. So, it is a heptane and start the numbering from the position closest to the branching. This is the position that is closest to the branching. So, this will be the numbering sequence of numbering. Now, there are 2 methyl groups, one in the 2 position and one in the 4 position. So, it is 2,4 dimethyl heptane. You cannot number from here because that end is farthest from the substituents which are the branching in this particular case. So, this is 2,4 dimethyl pentane, heptane. The di essentially indicates there are 2 methyl groups. If there are 3 methyl groups, for example, let us put one more methyl group here. This would correspond to, this particular molecule would correspond to 2, 3, 4 trimethyl heptane. So, di, tri, tetra, penta, hexa and so on indicates the same substituent occurring in more than one time. If it is occurs twice, it will be di, it occurs thrice, 4 times, 5 times and so on, as many number of times as possible if it occurs. That is the prefix that is given to the nomenclature in this particular case. So, if you were to name this particular compound, let us consider this simple molecule. The systematic nomenclature would be, the longest chain is C4 chain, 1, 2, 3, 4. So, this is butane, and if you consider on the butane, on carbon number 2 and carbon number 3, there are dimethyl substituents. So, 2, 2, 3, 3, tetramethyl butane would be the name of this particular compound. In the 2 and 2 position in the same carbon, namely carbon number 2, there are 2 methyl groups. So, 2 and 2 dimethyl, 3 and 3 again dimethyl. So, totally 4 methyls are there, that is why it is tetramethyl compound. So, tetramethyl butane is the name of this compound, and the 2 and 2, 3 and 3 indicates the position of the methyl groups in that particular structure in terms of the nomenclature that is being given. So, if 2 or more identical groups are present, then you give the prefix di, tri and so on, depending upon how many number of identical substituents are present in the system. Now, suppose if 2 side chains of equal length are there, then you have to select the one with the more branching. That is illustrated by this particular example. Let us, for example, take this molecule. If we consider this molecule, this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This will be 10. If you start from numbering from here, this also would be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, now you have a problem of whether to start the carbon chain numbering from here or carbon chain numbering from here. Now, the one, these are equal length, carbon 1 to carbon 10 here, carbon 1 to carbon 10 here, they are equal length. However, if you consider the branching, this has more branching. This has 2 methyl groups in the branching. This has only 1 ethyl group in the branching. So, start with the carbon which has the more number of branching in the chain and number accordingly. So, this would be corresponding to 3,3 dimethyl, this is a C10, so it is dodecane. Sorry, this is a decane. Dodecane will be C12. But in the 5 position, if you look at, there is a butyl group which is 1, 2, 3, 4. There is a butyl group which corresponds to this. In the butyl group, in the 2 position, starting from number 1, 2, 3, 4, this is a butyl group. In the 2 position, there is an ethyl group. So, this would be 5, 2 ethyl butyl, 3,3 dimethyl decane. If you start numbering from here to here, that will give more numbers in terms of the substituents that are present here. The sum of the numbers should be minimum. So, this is a systematic way of giving a nomenclature for this particular compound. Let us take another molecule. Let us take this particular molecule. This has 1, 2, 4, 6, 8, 10, again decane. It is a decane system. If you look at the numbering, in the 4 position, there is a ethyl group. In the ethyl group, in the 1 position, there is a methyl substituent present here. So, 4, 1 methyl ethyl, that corresponds to the branching here. 1-methyl ethyl is the branching that goes here. In the 5 position, you have again 1-methyl propyl. So, this is a hyphen here, 5 1-methyl propyl. So, in the 5 position there is a 1-methyl this is the methyl group and this is the propyl chain as attached to the methyl group, for example. So, 4 1-methyl ethyl, 5 1-methyl propyl dodecane, decane is the name of the compound. It is a C10 chain. There are 2 branching chains that are there. Each of the branching chain is first given the primary number to which the main chain is attached to. It is attached to the 4 position and it is also attached to the 5 position, the 2 branching chains. Now, what is the branch is described within parenthesis. In the 4 position, there is a 1-methyl ethyl group here. It is actually an isopropyl group, but isopropyl is not an IUPAC nomenclature. So, it is mentioned as 1-methyl ethyl group. Then in the 5 position, you have a 1-methyl propyl group. This is actually an isobutyl group, but you do not mention it an isobutyl group in the, or it is a 2-butyl group is what is represented here, but that is represented as a 1-methyl propyl chain is what the longest chain is here. So, 1-methyl propyl decane is the correct systematic name for this particular compound. Now, this is as far as the saturated hydrocarbon with the branching and so on is concerned. The nomenclature goes like this. Now, whenever you have functional groups are the ones which contains the either a carbon-carbon double bond or a triple bond or a functional group like oxygen, nitrogen, phosphorus, sulfur and so on are present in the organic molecule. The order of preference of functional group with the increasing order of preference, if it is written, then it is carboxylic acid which has a higher preference compared to sulfonic acid which has a higher preference compared to an ester functional group which has higher preference than a acid chloride. You can simply mention it as an acid halide. X is a halogen. It could be chlorine, bromine or iodine. Then comes the amide functional group. Then comes the cyano functional group, which has a higher preference over an aldehyde functional group, which has higher preference than a ketonic functional group and higher preference than a hydroxy amine functional group, then a C double bond C and a C triple bond C kind of a functional group. So, this is according to the IUPAC nomenclature. If you have a carboxylic acid functional group in the molecule and a hydroxy functional group in the molecule, the carboxylic acid functional group gets a higher preference. The molecule is named as a carboxylic acid and not as an alcohol. I will simply explain this with an example. If we take a simple example like this compound can be either named as an alcohol or it can be named as a carboxylic acid. According to the IUPAC rule, this gets the higher preference in terms of the preferential treatment of the higher order of the functional group compared to the hydroxy. So, this is simply named as 1, 2, 3, 4. It is a butanoic acid. With the space between butanoic and acid. All the carboxylic acids are named as oic acid. It can be methanoic acid, which is a formic acid. to, for example, this would be propanoic acid. So, you write propan, oic is the suffix that is added, and separately acid is written. That is how the carboxylic acids are named. So, this has a substituent in the 3 position. So, this would be 3 hydroxy butanoic acid. You do not have to say 1 butanoic acid, because carboxylic acid cannot be in the middle of the chain. It has to be always in the 1 position only, because it has the highest priority. So, you do not have to name the number corresponding to this position. So, 3 hydroxy butanoic acid will be the correct nomenclature for this particular one. Not, it is not, for example, four carboxy butane to all. This would be a wrong number. This is not giving preference to the carboxylic acid functional group. It is giving preference to the alcohol functional group, which would be wrong according to the first rule of the IUPAC in terms of the functional group. Somehow the functional group gets higher priority than the others. So, that has to be taken care of carefully in naming the organic compound. Functional groups such as phenyl, which is C6H5, which is this particular group. This is the benzene without a hydrogen. C6H5 would be the phenyl group. Halogens, alkoxy, they always come as prefix substituent. So, what is meant by prefix substituent? Let us take the example of let us say X is equal to bromine. Now, you can call this as butyl bromide or bromobutane. The systematic nomenclature tells you that this has to be 2-bromo butane. So, this is the correct nomenclature for this particular compound. Similarly, if you consider this particular compound here, this would correspond to methoxy. Which methoxy? 1-methoxy propane. So, this would be the systematic nomenclature for this one. So, these functional groups are always added as prefix functional group and not as the suffix functional group in the systematic nomenclature of. We have a carboxylic acid, the suffix is oic acid. If it is a sulfonic acid, then you call it as sulfonic acid itself. If it is a ester functional group, you call it as OAte as the suffix in the compound. Let us, for example, take the simple example of, let us call this as CH2CH3. So, this would be essentially ethyl. This is alcohol part is first written, and then it is actually ethyl acetate, but acetate is called ethanoic acid. So, ethyl ethanoate, this is what is represented by the OAte suffix that is given to the nomenclature. So, the alcohol portion is given first, space is given, and the carboxylic acid portion is mentioned as ate. So, this is Ethyl ethanoate is the name of this compound. Suppose if you want to call this particular compound I am specifically mentioning because this is a one butyl. You have to number the position where the butyl group is attached. It is attached to the first carbon, so it will be one butyl derivative, not two butyl or other substituted derivative. Butanoate. This molecule has a very pleasant flavor, this banana flavor. This is widely used in the perfumery industry and the food flavoring industry, for example, as a banana flavor. That's why I mentioned this particular compound. The point is that the butyl group is mentioned at the positional numbering corresponding to the attachment to the oxygen, which is one position instead of two position or three position, for example. And it is a butanoic acid derivative, so it is butyl butanate is the correct nomenclature for this particular systematic nomenclature of this particular compound. COX, let us say for example COCl carbonyl acid chloride, this would be oil chloride. If you consider this would be ethanoyl chloride. Propanoyl chloride, butanoyl chloride, and so on. The CN group is considered as a nitrile group. For example, this is a C5 derivative. So, this is pentane nitrile. Which pentane nitrile? This would be one pentane nitrile. You can also have isomers of this. This would be 2-methyl butronitrile. So, the longest chain is taken as the C4 chain. The substituent is the methyl substituent. It is a butyric acid derivative, so it is butronitrile. It will be 2-methyl butronitrile because numbering starts from here. So, it is specifically you need to mention pentanitrile or butronitrile and so on properly by taking cyano group as part of the carbon chain in terms of the length of the chain that is being considered. Now, an aldehyde functional group always ends up with a suffix al. This is butanal. You do not have to number the aldehyde because aldehyde group always comes as the end of the chain. So, butanal should be fine. You do not have to say one butanal because there are no such thing as 2-butanal. If you consider the isomer of this, then it would correspond to the 2-methyl substituted propanal. So, this will be 2-methyl propanal. So, the aldehyde substituent comes as the suffix al. The keto functional group comes with a prefix oxo. This is either called oxo or it is called one depending upon whether it is given the highest priority in the compound or it has a second priority. I will give you two examples of this. Now, let us say for example, this is a ketone. There are no other functional groups present in the ketone. The longest chain is 6 carbon chain. So, this is hexane one. But then you have to mention where the carbonyl functional group is present in this particular system. So, you have to say the position where the carbonyl functional group is. So, this will be hexane 2 one. One corresponds to the ketone. The 2 corresponds to the position where the ketone is present in the long chain. So, it is hexane one. This is also a ketone. It has a substituent. So, if you consider the nomenclature, numbering starts from here closest to the substituent. So, this is a hexane 3 one, but there is a functional group in the 2 position. So, this would be 2 chloro hexane, you do not need a hyphen here, 2 chlorohexane connected together, there is no gap here, space between chloro and hexane is not there. So, this would be 2 chloro 3 hexanone. So, that completes the nomenclature of this particular compound. So, here you are actually naming it as a ketone compound. Suppose if there is also a carboxylic acid present in the molecule, then it has to be named as a carboxylic acid. So, one cannot use the suffix "one" for the keto. Under those conditions, one would use oxo as the substituent. Let us take this example. Now, this is a carboxylic acid very clearly, because the highest priority goes to the carboxylic acid. It is a pentane carboxylic acid. So, it is a pentanoic acid, but then there is also a substituent present, which is the functional group that is present in the position. The position number goes in this fashion. So, this is 4. So, this would be 4 oxo pentanoic acid. So, the correct nomenclature is 4 oxo pentanoic acid. This would be the correct nomenclature of this particular molecule, 4 oxo pentanoic acid. So, whether you use oxo or one depends on whether you are naming it as a ketone, or if there is a higher preference to another functional group, the one does not come into the picture because you do not name it as a ketone. In this particular instance, for example, you have to name it only as a carboxylic acid. So, pentanoic acid is the correct nomenclature for this, but then you have to specify the ketone position as an oxo, 4 oxo pentanoic acid is the correct nomenclature for this compound. If it is an alcohol, you call it as OL, end it up with OL, all. Let us say for example, this will be methanol. This would be ethanol. This would correspond to 2-methyl, this would correspond to, this is 1-methyl propanol. am sorry, there is longest chain is butane. So, this is butane 2-all is the correct nomenclature for this. You have to worry about the nomenclature involving the longest chain. So, the longest chain is a butane chain. So, this is 1, 2, 3 and 4. So, the hydroxy is in the 2 position. So, it is 2-butanol. If you consider this molecule here, the longest chain is a propane chain. This is 1, 2 and 3. This is the longest chain here. So, this would be 2-methyl propan 2-all. The position of hydroxy is indicated as 2-all because it is in the 2 position. There is also a substituent which is a methyl substituent. So, is 2-methyl propanol is the correct nomenclature for that particular compound. So, systematic nomenclature of aliphatic compounds is what we have seen so far. Aliphatic acyclic compound is what we have seen so far. We can look at the cyclic compounds also. This would be cyclopropane, this will be cyclobutane, cyclopentane for example, cyclohexane. So, you add the cyclo as the prefix and count the number of carbons and name it as that many carbon number. This would be cyclohexane. So, the nomenclature is very similar to the propane, butane, pentane and so on, except the prefix is added as cyclohexane. This would correspond to cyclohexene. So, the olefin is always ending up with the suffix which is the -ene suffix. If it is an alkyne, then you end up with YNE. If it is a triple bonded compound, it will end up with wine, YNE. Let me give a couple of examples of that to illustrate the point. If you take this compound, this is an acetylenic compound and it is a C7 chain. So, it is a hepta. You have to specify the position of the alkyne. So, start from the position where the lowest number goes to the alkyne, 3-ine. So, this would be hepta 3-ine is the correct nomenclature for this particular compound. If it is a olefinic compound, this is a penta 2-ene. So, the ene and ine are the suffix for the alkene and the alkyne type of compound. If it is in the form of a cyclic system, you write the number cyclo as a suffix, as a prefix for example to the nomenclature. This would be cyclohexene. So, if you were to name this particular compound, the alcohol gets a higher priority compared to the olefin and the alkene, please remember that. So, the numbering goes like this. So, this will be cyclohexane 1-all, but it is not a hexane, it is a hexene. So, it is a cyclohex 2-ene 1-all. So, the correct nomenclature will be cyclohex 2-ene 1-all. This would be the correct nomenclature for this particular compound. It specifies both the position of the unsaturation, which is the double bond here, which is in the 2 position with respect to the hydroxy. The hydroxy itself is in the 1 position, so it is a hexane 1-all is the correct nomenclature for particular compound. if we have to name this particular compound, this is always given as a suffix. So, this would be chloro. Which chloro derivative? This is 1, 2, 3, 4. This would be 4 chloro butene. So, that would be the correct name for this particular compound. The ene comes to a higher preference compared to the chloro, so it is named as a chlorobutene. Amine compounds are, this is 1, 2, 3, 4, this is 1 butan amine or butan 1 amine also you can say, butan 1 amine. So, amine compounds are given as amine itself. If you compare these two compounds here hydroxy gets the preference, so it is named 1 in the hydroxy and 2 ene in terms of the olefin. But in this compound, the preference goes to the olefin and chlorine gets the least. So, this is actually 3 chloro cyclo hex 1 ene. That is the correct nomenclature. So, pay attention to the preferences that are given to the functional group. Alkyl functional group, phenyl functional group and so on are getting the prefix with the lowest priority, whereas functional groups like carboxylic acid, hydroxy functional group get a higher preference compared to olefins and alkanes in the nomenclature, system of nomenclature. In case of aromatic compounds, benzenoid compounds for example, benzene, one can write benzene like this or like this, they are equivalent representation, do not get confused. This would be methyl benzene, also known as toluene. This is a 1,4 disubstituted benzene derivative. So, this would be 1 ethyl 4 methyl benzene. The substituent, alphabetically this has a higher order compared to E comes before M. So, this is given number 1 corresponding to ethyl E, this is given 4 corresponding to M, which comes at a later in the alphabetical series for example. So, this should not be named as 4 ethyl 1 methyl toluene, 1 methyl benzene. This is a wrong nomenclature. Whichever substituent has the alphabet that has a higher priority in the alphabet series comes first, and that is given the higher number compared to this. If we consider this, the numbering is given such that the lowest number goes to the, sorry, this is a 4 position. So, this would be 1 chloro 2,4 dinitro benzene. The other hand, if you consider this compound, this would be named as 1, 2, 3, 4. This would be 2 chloro 4 nitro 1 methyl benzene. So, this is 2 chloro 1 methyl 4 nitro benzene, that gives the substituents the lowest number and not the other way around. It cannot be, for example, 1 chloro, 2 methyl, 5 nitro, that will give a higher number in terms of the functional group numbering compared to this particular number here. Phenyl is always taken as a substituent. So, if you have to name this particular compound, this would be 1 phenyl. There are 4 carbon units, 1, 2, 3, 4. 1 phenyl butane is the correct nomenclature for this particular compound. If you consider this particular compound, this is pentane. So, this is 1, 2, 3. So, 1 phenyl. This is a bromo, 2,3 dibromo. So, bromo comes first before 2,3 dibromo, 1 phenyl, 1, 2, 3, 4, 5 pentane. So, it is named as a pentane derivative with the bromine in the 2 and 3 position and phenyl in the 1 position. So, it is 2, 3 dibromo, 1 phenyl pentane is the nomenclature for that particular compound. This compound is simply known as cinnamic acid. Colloquial name is cinnamic acid, not trivial name is cinnamic acid, for example. But if you were to name systematically this particular compound, the numbering starts from here. So, this would be 3 phenyl, propa, in oic acid. So, it is a propenoic acid. So, the position of the propenoic acid is at 2 position propenoic acid. In the 3 position there is a phenyl group. So, it is a propene 3-oic acid, phenyl propene 2-oic acid is the correct nomenclature for this. How about a compound like aspirin? Let us take this simple compound which is acetyl salicylic acid. Acetyl salicylic acid is a trivial name. This would correspond to 2-acetoxy benzoic acid in terms of the nomenclature that goes for this particular compound. So far what we have seen is a systematic nomenclature of simple organic compounds. Now, let us move on to the next topic, namely the isomerism of organic compounds. Isomers are compounds having the same molecular formula but different structures. Iso means same, mers means essentially the same building block is what is used. In other words, the molecular formula will essentially be the same and structurally they will be different. The isomerism, you can have structural isomerism where the structure itself is very different for different compounds that in the isomer series, or you can have stereoisomerism. Stereoisomers, the structure will be essentially same, the connectivity in the 3-dimensional manner is different. So, this is essentially same structure, 3-dimensional connectivity is different. The stereoisomers, you have 2 types of stereoisomers. One stereoisomer is known as the geometrical isomers. The other one is known as optical isomer. We will come to the geometrical isomer and optical isomer a little later. For the time being, let us classify the structural isomers as chain isomers, positional isomers, functional isomers, and finally metamers. Now, if you consider a carbon chain which is containing 5 carbons, you can have the carbon chain in a linear fashion like this. This would be one possibility. You can have a carbon chain which is going to be like this with a branching. You can also have carbon chain which has 2 branching, for example, like this. So, if you take a molecule of pentane which will be CH3, CH2, 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 CH3, you can have a normal pentane, N-pentane, or you can have what is known as isopentane, or finally neopentane. Molecular formula is same, only the carbon connectivities are different, so that constitutes the chain isomers. So, if you have more carbons in the chain, the number of possible isomers also keeps going up, because you can have branching at various positions. For example, you can have, this is octane 2, 4, 6, 8, there are 8 carbons in this chain. So, this is octane. This is an isomer of the same compound. This is also an octane, 8 carbons are there, but this is a highly branched octane. So, this is called isooctane, for example. So, the chain isomer essentially arises because of the possibility of having substituent as a carbon. So, the more longer the chain it is, the more number of isomers that you can have in this particular. Positional isomers are essentially the position of the functional group will be different. Let us take, for example, a pentane chain or a hexane chain. This particular case, heptane chain is what is taken. If I put a hydroxy functional group here, this will be heptane 2 all, because the position of the hydroxy functional group is in the 2 position. Suppose if I put the position of the hydroxy functional group in this position, this will be heptane 3 all. I can go to heptane 4 all also. So, this particular position will be heptane 4 all. So, all of this constitute the positional isomers in terms of the position of the functional group that is being present in the system. So, if you consider similarly, this is a 2 hexanone, whereas this would be three hexanone. So, you can have either 2 hexanone or T hexanone, which corresponds to the positional isomers of the functional group that we are talking about. Functional isomers are isomers which have different functional group, but the same molecular formula. We consider these 2 molecules, one is an aldehyde functional group, the other one is a ketone functional group. Both of them are C3 carbon molecules only. So, that constitute essentially the functional group isomerism in terms of the positional, the type of functional group that is being present in the system. If you take the alcohol and the ether, for example, these are also functional isomers. One is an ether, the other one is an alcohol. Both of them have the same molecular formula, for example. If you consider a nitro compound, A nitro compound can be, this is an alkyl nitrite, this is a nitroalkane. So, these also constitute the so called functional isomers. Functional isomers are those where the functional groups are different, otherwise essentially the molecular formula is same. Metamers, when you have, let us say for example, two alkyl groups attached to a common atom like oxygen in this particular case, you can have isomers of this kind. This is diethyl ether, whereas this is propyl methyl ether. So, these are again isomers. The position of the oxygen is different in the chain. So, these are called metamers. So, what we have seen in this particular lecture is the systematic naming of simple organic compounds using the IUPAC nomenclature method, International Union of Pure and Applied Chemistry nomenclature method. Also, we have briefly introduced the concept of isomers, where the molecule has the same molecular formula, but different type of structures. Examples are given for these 4 types of isomers that are present in the organic molecule. We will deal with the geometrical isomer and optical isomer in the next slide, next lecture. Thank you very much for your kind attention.